Hello everyone, today I will discuss evil elimination reaction and its mechanism. So first we will discuss why when it is possible. It is only possible when the alkyl halides which can form the stable carbon like tertiary allylic and metallic halides. If you have alkyl halides which can form the stable carbon, so then there will be the even elimination like that. If like example, if you have this benzylic carbocation, then after removal of this chlorine there will be formation of this stable carbocation due to the conjugation of this carbocation with this phenyl ring. In the similar way, if you have allylic halides, then after removal of this chlorine, you will get this stable carbocation due to the conjugation of this carbocation with this double bond. So in the similar way, if you have tertiary alkyl halides like this, if you have tertiary alkyl halides, then chlorine will be removed and then carbocation will be formed like this. This carbocation will form and this carbocation is stabilized by the hyperconjugation of these methyl group and hyperconjugation of this hydrogen. So if you have any of these alkyl halides, then there is the possibility of formation of product by the even elimination. So second question comes, what is the requirement for the even eliminations? So for the even elimination reactions, we don't require strong base with high concentrations, and usually polar protic solvents like water, alcohol are sufficient for these reactions. Okay, so now we will discuss the mechanism. So we have this tertiary butyl alkyl halides, we have water, then there formation of this alkene and removal of this Br negative and this protonated water. So what is the mechanism for this the formations? So first will be the slow step, that will be the rate determining step, removal of this bromine, and this is the reversible also. Bromine will be removed, and then we have water, and this water will obstruct with this hydrogen, and this bond will be moved here, and this will be faster, and what we will get this alkene and protonated water. Okay, so this is a mechanism. This is a slow step, rate determining step, removal of bromine, and the second step is the elimination, removal of proton. This is the first step. So now we will try to understand in which will be the rate of reaction faster. So it depends, rate of reaction depends on the relative stability of the carbocations. So as you know, when the bromine will remove, there will be the formation of this first carbocation. First here this bromine will remove, then the first will be the formation of carbocation. If you have more stable this carbocation, then there will be the more and more faster rate of reactions. So uh, uh, tertiary benzylic and allylic benzylic will have the highest rate of reaction because these carbocations are more stable. After we have the secondary benzylic and secondary allylic, these two carbocation will form after removal of halides, then there will be the similar rate of reaction. In the similar way, if you have primary and benzylic and primary allylic, both will have the similar type of rate of reactions. After that, allylic will have the least rate of reaction for the even eliminations. So this we have discussed the stability of the even rate of reaction of the even elimination basis on the formation of stable carbocation. This is the for only similar. If you have given the similar alkyl halides like bromoalkyl halides or chloroalkyl halides or iodoalkyl halides, similar if the questioner if the question has given in which you have the alkyl halides having the same halogen group. So the rate of reaction will be deciding factor, but will be the rate of for the rate of reaction is the stability of the carbocation. So now the cases come when you have different type of alkylides. One is the iodoalkyl, second is the bromoalkyl, third one is the chloro or fluoro. In which alkyl halides will be the rate of reaction faster? So in that case, iodoalkyl halides will give the fastest rate of reaction. The second bromo, chloro, and fluoro. What is the reason? Because iodo is a bigger group and bond is weakest. So in the iodoalkyl halides you will get the fastest rate of reaction, and after that bromoalkyl halide, after the chloro, and the least rate of reaction will be in the fluoroalkyl halides because this is a stronger bond. So by another example you can see when you will move in the down in the periodic table, down in the periodic table, halogen group size increases and the bond becomes the weaker. So alkyl iodoalkyl halide will be the will give the fastest rate of reaction for the even elimination. So then there is another possibility in the even elimination mechanism, that is a possibility of the rearrangement of the carbocation is possible. So that we will try to understand in this example. If you have these alkyl halides, will duration is ignored, we will get this chlorine will be removed, Cl negative will be removed, Cl negative will be removed, and this carbocation we will get. So in the two position we, this is 1, this is 2, in the two position we have this methyl group. So this methyl group can be shifted here. So after shifting of this methyl group we will get this carbocation. So why this shifting happened? This carbocation is least stable comparison to this carbocation. This carbocation is more stable. This is the more stable carbocation. More stable carbocation. After rearrangement, this is before rearrangement. This is the less stable carbocation. So if you have less stable carbocation before the rearrangement, then there is a possibility of rearrangement and you will get the more stable carbocation. And after getting the more carbocation, there will be the removal of H positive and you will get the alkene. So when you, if you have some compound, then there is a possibility of even elimination mechanism and you are getting some carbocation, and if you have adjacent methyl group and after 1 to methyl shift, then there is a possibility of formation of more stable carbocation, and then there will be the 1 to methyl shift and you will get the final product after the 1 to methyl shift and this alkene. So some other question rises by discussing this even elimination mechanism. So what is the questions? Question is, so as we have studied in E2 mechanism, after E2 elimination there is the formation of the Z product. There is the possibility of two product formations. Either it will form the Z rule or it will give the Hofmann product. So in the even elimination mechanism also, the final product will be the follow the Z rule and you will get the more substituted alkene as a final product. Okay, and the second, as we have already studied in the E2 mechanism, there is a formation of the trans alkene. So in that case, by studying the stereoselectivity, we have understood in E2 elimination there is a trans is a major product. In the similar way, in the E1 also the trans alkene is formed majorly. And in the third, what we have studied, is there any stereoelectronic effect? In the E1 elimination, there is a no stereoelectronic effect, as we have studied in E2 elimination, because in E2 elimination there is a requirement of anti-periplanar. So there is a stereoelectronic effect. You can see my previous lecture for the stereoelectronic effect in the E2 elimination. So there is a no possibility of stereoelectronic effect in the E1 eliminations. Why it is not possible? Why it is not required? Because in this mechanism there is no anti-periplanar arrangement is required. There is only requirement of a planar carbocations for the E1 elimination mechanism.